Okay, so welcome everyone to today's IMP One World Mathematical Physics Seminar. It's my great pleasure to introduce Wojciech Dybalski from Adam Mickiewicz University in Poznan. And the title of today's presentation will be Interacting Massless Excitations in 1+1 dimensional QFT. So as usual, the seminar will be recorded and you will be able to watch it again on our YouTube channel. And I'm now very happy to leave the floor to Wojciech.
So thank you very much for the possibility to speak here. Indeed, my talk will be about interacting massless excitations in two-dimensional quantum field theory. So as a motivation maybe or introduction, let me mention two riddles or puzzles concerning such excitations. First of them concerns Wigner particles. Wigner particles for this talk are excitations with a sharp mass, that is, where mass is an eigenvalue of the relativistic mass operator. And in a joint work with Yota Nimoto, which is already 10 years old, we gave examples of relativistic wedge-local models in which two-particle S matrix turned out to be non-trivial and unitary on the Hilbert space of a model. So the puzzle is that asymptotic completeness holds already at the two-particle level, so one can ask with, intuition from quantum mechanical scattering, where are all the n-particle scattering states for n larger than 2? And this will be something I will try to explain in the first part of my talk. The answer lies, in fact, in dispersionless motion of massless excitations in two-dimensional scattering theory, in two-dimensional quantum field theory, and in the peculiar scattering theory, which actually was developed already in the 70s. But the main reason of this introductory part of my talk about Wigner particles and recalling these old works will be to prepare grounds for the second puzzle, which will be about infraparticles. So for the purpose of this talk, an infraparticle is any excitation which is not a Wigner particle. So it is, one can say, an excitation with a fuzzy mass, because its mass is not an eigenvalue of the mass operator, so it's somehow fluctuating. To formulate the puzzle, let me recall some standard wisdom. I think most of you agree that the free field theory should have scattering matrix equal to 1, a trivial scattering matrix. Maybe it is less well known, but it is a fact that massless free field in 2 dimensions contains infraparticles. And it is kind of folklore if you read about infrared problems, is that for infraparticles, we don't know exactly what scattering matrix means. We don't have a canonical scattering matrix. So of course, there is some tension between the statements. If we don't know what scattering matrix means, how do we know that it is equal to 1 in 2-dimensional massless free field? And in a rather recent work with Jens Mund, we try to substantiate this concern, and I will try to persuade you that indeed exotic vacuum structure, infrared vacuum structure of this model can affect an interaction which coexists with linear field equations. It will consist only in exchanging phases depending on some charges, but there appears to be some effect. Okay, so summing up, in the first part of my talk, I will discuss scattering of Wigner particles in 2-dimensional massless quantum field theory. And this will provide a basis to motivate our scattering amplitude for infraparticles. And the last part of the talk will be an outline of a computation of this non-trivial scattering amplitude in two-dimensional massless free field theorem. I'm going to work in a setting of wedge-local quantum field theorem, maybe not local, to which maybe you are more used to, but it is simpler and it also admits more non-trivial examples, which I would like to mention as we go on. So the story goes as follows. I pick some von Neumann algebra R, and I declare it to be the algebra of all observables localized in the right wedge of a two-dimensional Minkowski spacetime. So this is, say, the algebra of all observables localized in W. Now I take the commutant of this von Neumann algebra R prime and declare it to be the algebra of all observables living in the opposite wedge W prime. Now I want to impose some conditions. So I would like to be able to shift my observables from one wedge to another wedge, say such a shifted wedge, and I insist that I want to have a group of unitaries whose adjoint action performs the shift. So a shifted von Neumann algebra will be my algebra of all observables localized here. And I want to have a property of isotony. Now, so since this shifted wedge is contained in the original wedge, I want my shifted algebra to be contained in the original algebra. Now, more than that, I would like this group of unitaries to have a joint spectrum of the generators contained in the closed future light cone, now in the Minkowski spacetime in momentum space, so to say. And I would like to have a vacuum vector, which is a ground state of my system and which is a simple eigenvalue, simple eigenvector. I mean, we have a simple eigenvalue at 0, and this omega is the corresponding eigenvector. Okay, so this is my setting in pictures. If you prefer a more formal definition, then this is what is called in the literature a Borcher's triple, which consists of a von Neumann algebra, a two-parameter group of unitaries, and a vacuum vector, which satisfies the property of isotony. As I told you, if I shift the von Neumann algebra by a vector inside the wedge, then I want to stay in the algebra, and I want the joint spectrum of the generators to be contained in the future light cone. And I want to have a vacuum vector omega invariant under U. And now a little piece of information which was not on the pictures. It should be cyclic with respect to R and R prime, and it should be unique. So now for those of you who are more familiar with the traditional Haack-Kastler setting and Haack-Kastler nets of C-star algebras or von Neumann algebras labeled by open bounded regions, well, for example, the R you obtain by taking the algebra generated by all operators localized in a wedge. Right, so that's the setting, and now I would like to move slowly to scattering theory. So first I have to specify what are the single particle subspaces in my Hilbert space in which everything is going on. So a natural choice are the spectral subspaces of these two branches of the light cone, which I call H plus and H minus. And well, they have obviously a sharp mass equal to 0. That's why I call them Wigner particles. What you maybe remember from the definition of a Wigner particle is that this should somehow correspond to an irreducible representation of a Poincaré group. It is not exactly like this here. If I had a representation of a Poincaré group, which is something I did not say explicitly here, then typically it would be very reducible on this H minus and H plus. So this two-dimensional Wigner particles are very composite, so to say, which is maybe part of a solution to the riddle which I told you at the beginning, that in the end, two particle scattering states will suffice to cover all the vectors in the Hilbert space in some models. And this is also the reason why these excitations are often called waves and not Wigner particles in the literature, but I will stick to the terminology of Wigner particles because waves is even more, let's say, unspecific. Okay, so we have single particle states, and now we would like to have a scattering theorem corresponding to them. So first thing you do, following the ideas like LSZ, is to define asymptotic fields. And this has been done for local theories by Buchholz, and a slight generalization to the wedge-local setting is by Yota Nimoto and myself. The scattering theory here is very simple compared to the massive case or compared to higher dimensions, because you don't need any comparison dynamics. You simply take an observable f from our R and you shift it in light-like directions and you try to get a limit. And it turns out that there are limits under our assumptions, and you call them asymptotic fields phi f. They have a subscript plus minus, which distinguishes the two light rays, and they have a superscript in or out, which distinguishes the incoming and outgoing case. And now again, to be after the picture a bit more precise, the definition of these limits involves certain ergodic averages or Cesaro means, if you like, but since they are not that terribly important, well, you need them to get a strong limit and not just a weak limit. You can define it in many ways. So that's why I have, by an abuse of the standard notation, I hide these averages in these shifts here.
Excuse me, Buchholz's paper probably was about four-dimensional QFT, or did it apply to two-dimensional?
So the story was, there was a paper in 1975 which Buchholz wrote, I think still as a PhD student, and then he went to CERN as a postdoc, showed this two-dimensional paper to somebody, some big guy, I don't remember, from particle theory, who said, yes, go ahead. And then he wrote this four-dimensional papers. That's an anecdote which I remember, but definitely there is a paper of Buchholz about two-dimensional case from 1975, when four-dimensional bosonic is 1977 and fermionic is a bit earlier, somewhere in between those two dates, I think.
Yeah, because certainly this picture does not apply to other dimensions, or am I wrong?
Yes. So 2 and 4 are covered in these papers.
Okay, thank you.
Okay, and of course, so here I gave you two examples. The remaining ones are constructed analogously. Now the properties of the asymptotic fields, they behave in a natural way under translations from the wedge, and more importantly, here we see this dispersionless motion. So if I take a vector from H plus, so let's say something moving to the right, and try to add to this another outgoing particle moving to the right, I don't get two particles moving to the right, but only one particle moving to the right. And similarly with the other direction. So this is why it only makes sense here to talk about left running and right running excitations. And therefore, we construct only two-body scattering states. So how to do it? I take a vector psi plus from the single particle subspace moving to the right by acting with some asymptotic field on the vacuum. I take a vector psi minus by acting with the left moving field on the vacuum. And now to get a vector which describes both particles, I act with a product of the two of them on the vacuum. And I can also obtain it using the approximating sequences of the asymptotic fields. The incoming scattering states are obtained analogously. So given scattering states, I can compute their scalar products of two outgoing vectors, and I see that this is the same formula as for simple tensors. So indeed, these are two independent excitations at asymptotic times, and also the translations factorize into these two factors. So that's why these vectors describe two asymptotic excitations, let's say, independent at asymptotic times.
So excuse me, so it seems there is no Fock space structure in this asymptotic space.
No.
Am I correct?
That's correct. This is a tensor product structure, usual tensor product of two factors.
Yeah, so this is quite different from other dimensions.
Yes. Okay, so I denote by H in the subspace of asymptotic of incoming asymptotic states, and by H out of outgoing asymptotic states, and I define and one can define the scattering matrix as a map which takes, say, the outgoing asymptotic state into the incoming one. And now we say that the theory is interacting if S is different from 1, and the theory is asymptotically complete if H incoming is equal to H outgoing is equal to the full Hilbert space. So I think that's the general formalism. And now the question is, are there any interesting examples? And we looked at examples which are popular at that time, let's say 10 years ago, which were constructed by Grosse, Lechner, Buchholz, and Summers using a kind of deformation which is similar to Riefel deformations. The idea is, of the story goes as follows. We start from a Boischer's triple with some scattering matrix S, which may be trivial. So we start, for example, from some kind of free field theory. And we take a matrix, deformation matrix QK, which is anti-symmetric in Minkowski scalar product and therefore symmetric in the usual sense. And now one constructs a deformed Wojciech triple with a new scattering matrix using a tool which is called warp convolution. So this is a very ill-defined integral at first sight. So here with alpha are simply translations, which we know. I translate my observable, but when the resulting function of P is integrated with a joint spectral measure of the energy momentum operator. So you try to integrate an operator valued function with a spectral measure. Of course, a very suspicious thing, but these authors managed to give it a meaning in terms of some oscillatory integrals. And they also checked that it changes the two-body scattering matrix in massive theories in 4 dimensions. What we did, we looked at massless theories in 2 dimensions, and not surprisingly, we also got that it changes the scattering matrix, so introduces interaction, where we got even a nice concrete formula for this change in terms of relativistic mass operator. But a more surprising aspect was that this deformation also preserves asymptotic completeness. Well, basically because what you have here is a unitary, so if original S is 1 on the entire Hilbert space of your model, then very deformed scattering matrix is also unitary on the entire Hilbert space. And of course, to start with, you need an asymptotically complete non-interacting theory in 2 dimensions, and the examples are provided by chiral conformal field theories. So why was it a surprise? Well, back then, there was a belief that in wedge-local quantum field theories, you cannot really study asymptotic completeness because you can construct at most 2 particle scattering states, because for scattering theory to work, you need to be able to separate particles by your observables, and you can separate at most 2 particles with 2 wedges, with 2 opposite wedges. So now a first way out here was the story which I just told you. Okay, let's go to massless 2 dimensions, where you have only 2 particle scattering states. We have only 2 particle scattering states in wedge-local theories. It suffices, so it's fine. But interestingly, later it turned out that there is also a way out in higher dimensions. My former PhD student, Max Duell, developed a natural scattering theory for massive wedge-local theories in any dimension. And later we managed to prove asymptotic completeness of the warp convolution models also in any dimension. But this is just a side remark. I don't want to enter into this because I wanted to keep this talk 2-dimensional and massless. Okay, so this is what I wanted to say about Wigner particles to prepare a basis for the second part of my talk, which will be about infraparticles. Let me recall, infraparticles are all excitations which don't have sharp mass, which means now in a new notation, so to say, that they do not live in the spaces H plus minus. The scattering states as we define them, therefore, do not make any sense for infraparticles. And the scattering matrix as we defined it also doesn't make any sense. So as a last resort approach, we can nevertheless try to define some kind of scattering amplitude using the approximating sequences, because that's okay, a finite time, this I can write in any theory. For infraparticles, it will converge to 0, but maybe we can arrange for some cancellations. So this leads to the following formula for a scattering amplitude. So here you can see this is the approximating sequence of an incoming scattering state. This is an approximating sequence of an outgoing scattering state. And this is a certain normalization, so that for Wigner particles, we just obtain a S matrix element like so. So for Wigner particles, if this scattering amplitude is different from 1, then also scattering matrix is different from 1. So we have interaction. And this observation motivates us to state the following criterion. Give me any two-dimensional massless theory, then I can try to compute the scattering amplitude, and if it is different from 1, then I say that the theory is interacting. Well, apart from this condition, we insist that it should be different from 0, because I think it would be a bit dishonest to claim interaction only because something gets 0 in all cases. And also we insist that this should be in modulus less than or equal to 1, because after all, that's the case for the usual S matrix. You don't want to get too far from the usual probability interpretation and so on. Now, to be completely honest with you, probably I should add that this formula star is not the only way for Wigner particles to get this expression. For example, I could drop this minus signs in the denominator, and then in the Wigner world, nothing would change. I would still get this expression. So why do I keep the minus signs? And a priori reason is that in this case, if I move to a single particle scattering, so to say, which means I drop all the black F primes and keep only blue ones, then you see that there is an automatic cancellation and I get 1. And I don't want to have one particle scattering, because I don't have something like one particle scattering in the Wigner world. Okay, so in the remaining part of my talk, I will try to explain or persuade you that the scattering amplitude is different from 1 in massless free fields. And for this reason, I have to recall some facts and notations about massless free field in 2 dimensions, which may be well known to you. It's textbook material. I don't know exactly which textbook we use, Abdallah and Rote about 2-dimensional models. Also the lecture notes of Telezinski and Meissner were useful, and papers by Acerbi, Marchio, and Strocki. The literature about this model is pretty large. One can tell the story as follows. We start from the 2-point function of the massive free field theory in 2 dimensions, which is a Fourier transform of Lorentz invariant measure. And now if you try to take the limit mass goes to 0 as a distribution in X, then it turns out that this is meaningful only on test functions whose charge, which is here the integral over all space, is equal to 0. And this is, of course, due to the logarithmic singularity of the invariant measure in 2 dimensions. But nevertheless, I can take the commutator function, which is the difference of the 2 two-point functions, and here the limit will exist on all test functions. So I can take advantage of this fact and define a symplectic form, which is non-degenerate on a symplectic space, which are real valued test functions divided from the range of the Klein-Gordon operator. Now, if I have a symplectic form and a symplectic space, then I can define the Weil algebra or CCI algebra in the usual way. I take some abstract symbols with such relations and call the algebra which is generated by this F. Let it be a C-star algebra. And I can also define the underlying Hack-Castor net labeled by open bounded regions by restricting to Weil operators whose support is in O. And I also have a representation of the Poincaré group in automorphisms of this F, which is inherited from the natural action of the Poincaré group on the test functions. Okay, so I have an algebra. Now it's still abstract. I want to have a Hilbert space for scattering. So I want to have a state, preferably a vacuum state. And it's also a standard definition how you construct a vacuum state in this model. You try to take a limit mass goes to 0 of the 2-point function, but on the Weil operators in the exponential form. Or in other words, you declare the state to give e⁻⁻⁴ the 2-point function if the charge is 0, or 0 otherwise, because, well, if this diverges, this exponential should give 0. It turns out to be a well-defined state, so I can move on to the JNS representation. It's irreducible and covariant under the action of the Poincaré group. Furthermore, it satisfies the spectrum condition, so everything looks like in free field, but still in several respects, it is not the usual free field. First, the representation is not regular, so we don't have a quantum field whose exponential would give this Weil operator, well, in a representation, so to say. And also the Hilbert space is not separable, so it is not the usual Fock space. Okay, so I have a model. Now I can ask what is the particle content of this model. Are the Wigner particles, are the infraparticles, and so on. For this, it is convenient to define a subalgebra A of this algebra F, which is generated by all the charge-free Weil operators. And then I can also define a subspace H0, which is created from the vacuum by all the neutral charge 0 operators, and its orthogonal complement are then charged particles. Then it's a simple fact that the spaces H plus minus, so the spaces of Wigner particles, all live in H0. So all Wigner particles have 0 charge in this sense. So if there are some charged excitations, and we have, in fact, this H charge is non-trivial. So if there are charged excitations, when they are not Wigner particles, they correspond to somehow to continuous spectrum of the mass operator, so they are infraparticles. As I mentioned at the beginning, it is known that the model contains infraparticles. I know it from a paper of Buchholz with a, say, intriguing title, Quarks, Gluons, Color, Facts or Fiction. In particular, it discusses this model. So it is not a new observation that there are infraparticles in massless free field in 2 dimensions, but a new observation is that these infraparticles have non-trivial scattering amplitudes. More precisely, we get a formula like so. The scattering amplitude is an exponential minus I half the product of 2 charges for F and G, the Weil operators. So now, if I chose these charges equal to 0, then the scattering, then this would be Wigner particles, and the scattering amplitude would be 1 as expected. But we also have some excitations which are not Wigner particles, and for them we have a let's say non-trivial effect. Perhaps one should say that excitations exchange phases when they collide. You can say it's a very weak effect because the scattering amplitude doesn't depend on momentum. But in two-dimensional models, there are other examples like the Ising model or Federbush model, where also the scattering matrix doesn't depend on momenta, and still it's considered non-trivial. Okay, so now I would like to say a few words about the proof of this theorem, which is basically a computation. I have to add a few words, perhaps again very well known to you from the chapter of textbook material. As we use the standard tool, which is the regularized two-point function. I take the original two-point function and I subtract some function b, which is equal to 1 at 0, in order to cancel this logarithmic singularity from the measure. I choose this function in such a way that while the original two-point function is infinite on charged test functions, the regularized one is always finite. Given this, I can define regularized big-ordered while operators. I basically divide my while operators by certain numbers which are non-zero and finite, and which are kind of expectation values with this regularized two-point function. But I should stress that the regularized two-point function does not give a proper state on a C-star algebra, so this is not really an expectation value. These are just some numbers here. I don't change the formalism, I change the generators in my algebra a little bit by dividing them by numbers in order to get convenient formulas. And the convenient formula I want is on a product of while operators and its expectation value. I stress that this expectation value, the outer one, doesn't have NLV. This is the real physical vacuum. And how do you compute it? Well, first you use the while relations to make one while operator out of this. Well, these are just numbers somewhere hidden here. And then you come back to this definition, and then you express the result again in terms of this regularized two-point functions. You get something like this, which is non-zero only when the total charge, the sum of all the charges, is equal to 0. So why do we want to have it? We want to have it because in our scattering amplitude, we have such expectation values, and basically what we want, what we need to study is the behavior under large translations of these while operators. So this formula tells you that this boils down to the behavior under large translations of these regularized two-point functions. And this can be, let's say, computed. One needs, to some extent, all possible directions, so time-like, space-like, and light-like, but they play a different role in the computation. So the most important is perhaps the time-like asymptotics, because all the non-triviality comes from a certain, let's say, tight I pi, which depends on the time direction, which comes from a phase of some complex logarithm. But it comes together with a logarithm of t, which diverges as t goes to infinity. But fortunately, in our computation, we also have space-like asymptotics, which also comes with logarithms. And fortunately, always logarithms cancel, and we are left with this IPi contribution. The least important, but the most complicated formula is for light-like asymptotics. But light-like asymptotics doesn't cancel immediately only because we have this ergodic averaging in our definitions of asymptotic fields. If we didn't have it, they would cancel immediately, but since it is there, they cancel only in the limit, and you have to worry a bit also about the light-like asymptotics. Right, so how the computation goes, that's the formula for the scattering amplitude. We pick as f and g the while operators, and we rewrite everything in terms of Wick ordered while operators. All the constants cancel between the numerator and the denominator, and apply a formula for the expectation values of while operators. Then one uses the lemma to study the behavior of these regularized two-point functions under large translations, and trust me, this is what you get. Okay, so I think I am slowly reaching the end of my talk. There is some outlook. For me, the most, let's say, intriguing question is if one can play a similar game in higher dimensions, for example, in 4 dimensions. Well, if I take the usual massless scalar field in 4D, then I will realize immediately that the two-point function doesn't have a logarithmic singularity. So the scattering amplitude will be 1, there will be no effect. But on top of the massless scalar field, one can construct a string local theory as follows. First, you take a function supported in a small region of a sphere, and now you define a string local field by integrating the usual massless free field over strings in directions dictated by this h. And then it turns out that the two-point function of this resulting object in fact has a logarithmic singularity, similar like in 2D. So it seems we are in business, we can try to play the same game. And after you compute, for a moment you are very happy because you get something non-trivial which has a similar structure as before, but now there is some function h which depends on directions of the strings and directions of propagation of the particles, which are a priori 2 different things. And after watching at it for a moment, you notice a problem. Namely, the real part of h is inevitably different from 0, and therefore, since the charges can have different signs, the modulus of the scattering amplitude will be inevitably, in some cases, larger than 1. That was, in fact, first noticed by Gass, Reiren, and Tipner in this work, which appeared in September, shortly after our paper. And that's basically the situation. So that's the third puzzle of my talk, which will not be resolved here. How to solve this problem in such a way that we again get something acceptable. So for example, a phase. Of course, it's easy to get 1. I can take massive string-like theory and I get no effect. One idea is to change the vacuum state to some, let's say, nicer state from the point of view of infrared problems. In the theory of infrared problems, people constructed over the years various infravacua which behave like a vacuum but have nice infrared properties. I started looking at some such states, but it's not easy to get the property you want for the scattering amplitude and in the same time positivity of energy in such a state. And I think it's quite important to have a, let's say, convincing argument. Okay, so that's the state of that's the situation here. Thank you very much for your attention.
Thank you very much, Wojciech, for this very nice presentation. And I now leave the floor to the audience for questions or comments. Yes.
May I ask a question?
Yes, go ahead, Jan.
So this 1 + 1 dimensional theory is of course quite reasonable and I mean standard. Now the last slide was devoted to a more speculative theory. I mean this string localized. Well, I mean it's is it a reasonable theory? Does it satisfy reasonable assumptions? So is it interesting enough to be considered a part of mathematical physics? Let me put it like that.
No, to my understanding, such models are in good shape. The papers by Reyren, Schroer, Mund of recent years about string-like quantum field theories, well, they don't consider exactly this one. Their favorite one is called an escort field. The escort field is basically a gauge shift in QED between two different gauges, between the Lorentz gauge and the axial gauge, but the formula is very similar to this one. And well, you can basically take a formula for a two-point function for this fields, construct a Weil algebra. It's a well-defined symplectic form. I'm not sure if it's non-degenerate. So in such details, one could ask questions, but you have a string local net of algebras in a translation invariant state. So here it is, of what I wrote here is of course a heuristic formula for an Outlook slide, but well, if I wanted to make it rigorous, you would maybe start from this and try to define it as a symplectic form and build a Weil algebra on that. It's true that the papers are not written in this language, but I see no obstacles. It doesn't seem more difficult than in the two-dimensional massless free field theory to construct the model.
Well, this theory does not have Poincare covariance.
This is correct. I think you have translation covariance. Well, yeah, I think you are right, but if you even rotate the string, then you may end up in a different sector. So possibly the vacuum is not Lorentz or rotation invariant, but in QED it's also like this in charged sectors. So I don't think it's such a big problem.
Well, in QED you have all sectors at the same time. So QED is kind of Lorentz covariant when you consider all of the sectors. No, I would be happy if you convinced me that these string localized theories are physical. I mean, but you still have to find an argument to convince me.
Well, I would say I have not been really involved that much in string local direction, but okay, so let's have a deal. If I write a paper about it in the future, I will try to be very careful both on mathematics and interpretation of these things. For me, it is more about here making a mathematical point, but you can have string locality, positivity of energy, and this sort of interaction in 4 dimensions. I think that would be something worth writing up if true, but I still don't have it because of a problem which I mentioned here on this slide, and I don't have a solution which would respect positivity of energy.
Thank you.
Thank you. Other questions or comments? So actually, I think I have a naive question. Can you come back again on the fact that your Wigner particles had to have 0 charge, right? So why was that? And was that somehow to be expected in the model you were considering?
Let's see. This part, it is. If this is expected in the model, where you expect to have some Wigner particles here, because inside this model there lives a theory which is obtained by taking derivatives of the field with respect to space translations, d mu phi. So this boils down to these functions which are not charged. So from this fact that we have this theory inside, it will reasonably create Wigner particles from the vacuum. So we expected that there should be Wigner particles, and that they will be neutral because these derivatives, as I said, are related to 0 charge in this sense.
Okay, thanks. Okay, other questions? Okay, doesn't seem to be the case. So let's thank again Wojciech for this very nice talk.
Thank you very much.